all these amazing talks. Just one more. So we've got José Samper, who's going to tell us about unbounded matroids.
Okay, thank you very much, and thank you very much to the organizers for the invitation. I don't know if you can hear me well. Good. So again, I start by saying that this talk is also jet lag friendly, because I guess many people are tired, as I am. I come from the University of Chile, and I'm going to talk at the Catholic University of Chile, and I'm going to talk about joint work with Jeremy Martin, who is at the University of Kansas, and Jonah Berggren, who is at the University of Kentucky. And I was going to make a joke, but no one did that today. So I've seen a bunch of pictures of talks where people put pictures of their collaborators, but I did my presentation with this very rough tablet, and I tried to embed a picture, but it lost the colors. So I decided to draw them. You know, if you've seen Jeremy, it's the guy with the glasses and curly hair. But okay, so I'm going to talk about unbounded matroids, and I'm going to give a slightly different definition of a matroid. So bear with me for a few minutes. But I want to talk about matroids on the ground set n, so the numbers from 1 to n. And the way how I'm going to think about them is in terms of a polytope in Rn. Okay, so polytope being the convex hull of finitely many points in Rn, and what this is as Graham was explaining today in the morning, these are convex hulls of vertices, all of whose coordinates are 0, 1, or characteristic vectors. And what I want is all the edges to be parallel to some ei minus ej, so a difference of standard basis elements. Okay? So I don't expect everybody to have seen this definition, but let's think of an example for a second. Okay, so I have the uniform matroid on 4 elements of rank 2. And what I want to do is I want to look at the convex hull of the characteristic vectors of the bases. So the bases are 2-element subsets. And these are going to live in R4. But they all, so the sum of the coordinates is always equal to 2, meaning that they live in a 3-dimensional subspace of R4. And so here I have 8 vertices. They're going to look like an octahedron placed in a 3-dimensional space. And the edges, for example, you can see an edge over here going from the vertex 0, 1, 0, 1 to the vertex 1, 0, 0, 1. And what this is telling me is that I replace the element 2 by the element 1 in my picture, and that means that this edge is parallel to E2 minus E1, which is a basis vector. So it's like a geometric way of encoding the exchange axiom. Okay? And what's very nice is that from pictures like this, which usually are high dimensional, but we get some sort of intuition by playing with geometry, we can learn a little bit, a lot about the matroid. For example, the vertices, as pretty much by definition, correspond to the bases. But if you've seen a little bit of discrete geometry at some point, for example, you can describe a polytope in terms of inequalities. I have so this polytope here has 8 triangles, and so you can define it in terms of 8 inequalities, which you can redundantly define rather easily in terms of the rank function. I'm not going to do exactly the exact details here. Let me just tell you the story, and if you want, we can talk about details through the entire week. That's one of the nice things about giving a talk on Monday. And then there are many other things that we can think about. So maybe in a polytope, you want to think about linear programming. And these are polytopes that are very interesting for linear programming because optimizing is quite easy, and this is quite easy on them. And this is essentially the greedy algorithm. Okay? So if you want, think of your favorite matroid cryptomorphism and try to see if you can understand it from a geometric point of view. Okay? So again, bounded polytope, convex hull of the bases, and And what I want to do is think about the matrix geometrically. So what I'm going to do is I'm going to define an alternative or an extension of matrix, and then I'm going to try to justify why this is a cool thing to do. But what I want to do is I'm going to define an unbounded matroid on N. And what an unbounded matroid on N is, well, I'm going to look at a polyhedron, and instead of looking at it in terms of convex hulls of polytopes, what I'm going to do is I want the polyhedron to be unbounded, and I'll show you an example in a minute. And I'm going to ask for a few conditions that are very similar to the ones that we ask for matrix. The first one, and this is technical and not too important, but I'm going to ask my polyhedron to have at least one vertex. So in this case, my polyhedra are, I want this to be a subset of Rn defined by linear inequalities. The second condition that I'm going to ask is, well, I have one vertex at least, and I want my vertices to still be 0, 1. So remember, in a matroid, the 0, 1, or the vertices are usually bases of the polytope, and what I want to do is I want to define something a little bit more like that. Or I want to keep that property. And then the third one is I want to still have the nice condition on the edges, because geometrically, that may say something interesting. And so there's many polyhedra in the world, and the very special thing about matroid polytopes and about matroids in general is this condition that edges are parallel to some EI minus EJ. Okay? So let me go with an example, and it goes by picture. So what I'm going to do is I'm going to look at this polyhedron over here. So now it's unbounded in some direction. That's hence the name unbounded. But it's a polyhedron. So now I still have a bunch of inequalities. If you look at it, it's 6 of them. It now has 4 vertices: 1, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, and 0, 0, 1, 1. But 2 of the, and there's 2 other red dots there that correspond to other 0, 1 vectors that are not vertices anymore. But the point is, they're going to go in an unbounded direction, and we can ask, so what are these objects? Okay? What I want to try to figure out is, well, this is a natural geometric definition. It's similar enough to a matroid, to the definition of matrix, except that we're considering unbounded polyhedra. It seems combinatorial. We don't know exactly whether this is a nice object to play with or not, but or at least not yet. I have not told you. But the main difference is, well, I'm not constraining myself to bounded universe. For geometric reasons, that makes sense sometimes. And what I would like to know is, well, can I actually think of these objects in a matroid theoretic sense? Do I get nice cryptomorphisms? Or, I mean, we had 3 questions in the previous talk, you know, like duality, cryptomorphisms, and minors. And what I want, or the nice question that I'd like to understand better is, well, what are these things? So a little bit of discrete geometry. If you have a polyhedron that is unbounded, any polyhedron, there is a very nice decomposition of this polyhedron in terms of something that is bounded and something that is a cone. So a cone is the set of positive combinations of a finite collection of vectors. And the point is, if I have any unbounded polyhedron, I can always decompose it as some bounded part that corresponds to the vertices, the green vertices that I'm drawing here, and some cone that corresponds to the unbounded directions. Okay? So it's written over there. I have my polyhedron. I have a Q, which is a polytope. It's a bounded thing. It's the convex hull of finitely many points. And there's a cone. And what that decomposition means is it's called a Minkowski sum. I take a point in Q, a point in C, and I add it. It belongs to P. So it's a collection of all sums of an element of Q and an element of C. So this decomposition is very special and interesting. So here I have an example of the decomposition, and we have a cone. That cone is always unique. It tells me in which, so the unbounded directions in which my polytope is allowed to go to infinity are encoded by that cone. The polytope is not necessarily unique. Okay? It can have many more vertices. It can be, so the polytope is highly non-unique. I need to use somehow all the vertices that exist in my polyhedron, but I can add many different things. For example, I could decide to add this pink thing over here, and the Minkowski sum is not going to change. Or I could make this way more intricate here in between. And so that's why the polytope over there is highly non-unique. You know that there's like a minimal thing that has to be there, but you could add many more complicated things, right? So the question is, well, if I have one of these unbounded matroids, do I get some nice relation to matrix theory, or can I actually try to understand a little bit of the combinatorics by playing with these? And the answer is yes. Okay? Yes? I cannot hear you.
Blah, 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 blah. Okay. So I just have a small question. So when you had this decomposition to this finite thing, and then a cone, like, you said you have a few possibilities about how you decompose this, right? Like, do you just care about the existence, or are there instances where you actually care about the particular choice you make?
I'll tell you an interesting, for matrix, this is actually interesting.
Okay.
And in many cases, yeah, so it may be that for a good reason or not, there's a convenient way of choosing the polytope and allowing a little bit more flexibility.
Okay, thank you.
So the idea is, well, I can look at the unbounded matrix, and I can look at the decomposition. So in the decomposition, I'm going to have a cone. That cone is going to correspond to a poset, a partially ordered set on the numbers from 1 to n. Okay, so maybe in my example over here, if you look at all the edges that are going in the infinite direction, they're all parallel. So there's 4 of them, they're all parallel. And for example, if we look at this red point here, what it is doing is it's replacing 2 for 1. So this edge here in the unbounded direction is the edge E1 minus E2. Okay? So as a partially ordered set, what this is going to tell me is I'm going to put a 1. So I'm going to force 1 to be greater than or equal to 2, and I'm going to leave no more relations between the other things. So the point is, the unbounded part is going to tell me a poset, or is going to give me a poset, and that poset is going to be given by the relative orders of the coordinates in this cone. That's a very beautiful theorem that is a codification of Postnikov-Reiner-Williams of basis of generalized permutohedra, if you know what that is. And then there's a polytope part. And I can wonder, well, what's this polytope? And in general, that polytope is not much. So in my example over here, it would be 4 points. And the question, or a natural question is, well, can this be a matroid? Or can I amass some interesting combinatorial polytope that has some sort of relation to matrix theory? And the answer is, it actually can. And there's many beautiful things that happen in between, but the main theorem that, or one of the big theorems that we proved in the paper with Jeremy and Jonah, is that if we look at all the 0, 1 vectors in this polyhedron, then they form a matroid. Okay? So if you like, if you want to discuss about crazy things that happen when you think about this. We have an entire week. I've been thinking about this structure for a long time, and I think that this should have many interesting applications, but I don't know exactly where to start. There seems to be too much. So let me give you a brief overview of what happens, you know, or what are the things that show up in this theory. So if I want to figure out what unbounded matroids are, well, these are matroids somehow associated to a poset. And the poset comes from the unbounded directions. It's called a poset cone, classical result, very beautiful. If you want to think of matroids, well, these unbounded things have an associated poset, and if you want to think of matroids, these are matroids over the antichain, a poset with no relations. And this is somehow related, so the fact that you have no relations is somehow related to the fact that you have a bounded object. Okay, so the relations in the poset that is underlying this thing tell you exactly how you can go to infinity in this geometric object. P, so if P is an unbounded matroid, you can think of this polyhedron, and it will be defined, for example, as a submodular function on something called the joint distributive lattice. I guess it's a bit related to what Peter was saying in the previous talk. But there's a very nice notion of submodular functions on a distributive lattice. And if you know what polymatroids are, one of the cool things is that you get a new cryptomorphism for polymatroids by choosing the correct poset. So instead of looking at an antichain, what I'm going to look is a partially ordered set in which I'm putting a bunch of these joint intervals. And if I want to play with this unbounded matrix, what I have to do is do matrix over a poset. So what is quite interesting is that, well, these things are going to have many new cryptomorphisms, or add new cryptomorphisms to the theory of polymatroids, many of them. So yeah. So let me tell you a little bit of interesting stories that are kind of related to this. But when we started thinking about this, we were thinking about Hopf algebras. But we started digging into the literature, and we found a few very interesting pointers to the past. So it seems like Rota obsessively asked the question of what's a matroid over a poset to many different people, and you can, it's not hard to find literature in at least two different times where these notions are discussed. So the first one is due to Fagel in 1980, and he calls, so he defines some objects called geometries over posets. And when you see what happened to that literature, it ends up with a lot of papers by Korte and Lovash, and these are things that are now called Fagel geometries. But they ran out of geometry, and they started talking about gridoids, which are, so they're very nice combinatorial objects, but they kind of lost a little bit of the matroid nice properties. And there are various notions. So the problem of what happens, or when they got stuck here, is that they tried to, or Fagel tried to come up with a bunch of notions of cryptomorphism and tried to figure out if this was a good definition. But he had two issues, and one of them is that as someone influenced by Rota, he was convinced that the right notion was to study simple matroids instead of matroids, and that makes the theory much harder. And in this case, it actually makes the definitions worse. And then there's another notion by Barnaby, Nicoletti, Pezzoli in the 1990s. Again, this is, if you read the paper, you see that this is a question that was posed by Rota. They talk about matroids over posets. These are objects that are contained in these Fagel geometries. And what ends up happening is that these unbounded matrices actually capture all of these things, both of these notions. And surprisingly, so there's this book by Fujishige on submodular functions, and this was kind of predicted by him. It's left as a comment. It might be interesting or not, but it was there, and so when we started studying them, we found out that similar notions have been studied in the past, but maybe not from the from the geometric combinatorics point of view, and so it seems to simplify a ton of old results, and I'd really like to be able to talk to Rota and ask him what was he thinking, or what was his idea behind these matrix over posits. But I would like to say this is a nice definition of matroid theory, in the sense that there's natural duality, similar to matroid polytopes. What one has to do is, again, flip the posit. If you were paying attention to the previous talk, it's similar to what the duality was doing there. And there's many different cryptomorphisms, in the sense that you can define matroids as objects satisfying something for many orderings on a set. And if you want to talk about unbounded matroids, you can produce many of the similar many of the similar axioms by thinking of objects satisfying a similar property for all linear extensions of the underlying posit. Yeah, so that's more or less the story. Let me quickly end by asking two questions that I think might be of interest. And I don't know exactly what to do with them, and maybe someone here is interested in one of them. So I have first a speculation, which is that there should be a good deletion and contraction theory. One might be able, or one might want to, or one might suspect that maybe the deletions and contractions are related to the order P. But the point is, it's a little bit more difficult than one would want, and the point is, or the difficult thing here is that the obvious deletion and contraction at the level of sets is not, or it's not really clear what to do, but when we have the geometry, the picture becomes a little bit clearer. So, so what we would do is, well, we start with an unbounded matroid P. We look at the matroid that is contained in this unbounded thing, the largest matroid contained in that thing, and we do have a posit, and then we do the deletion contraction first on the matroid, separately on the posit. That's going to give us a different posit, and then take a new Minkowski sum. So to me, it seems like this is an interesting notion of deletion contraction that is or has not really been studied. It seems to check some of the nice properties that one would want from such a deletion contraction theory. But so far I'm only able to call it a speculation. But I suspect that there's a nice notion of a Todd polynomial and many nice ways to compute invariance, which, if you remember what I said before, for example, will apply to polymatroids. And the second speculation is a little bit more geometric, right? So in matroids, we're able to use matroids to study topology of complements of hyperplane arrangements. And if we orient the matroid, we can talk about the complement of the hyperplane arrangement and a little bit of the geometry of the complement of the hyperplane arrangement. So that's a more polyhedral geometry in spirit topic. But the point is that with unbounded matroids, we get a theory that is analogous to polymatroids, which actually capture the geometry of subspace arrangements. And when we look at the new cryptomorphisms, we get new notions, for example, of the lattice of flats, geometric lattices, closure operators. And it seems like it would be a good idea to develop an oriented theory for these beasts over here. If anybody's interested in oriented matrix or oriented theory, there's a very nice theorem of de Longueville and Schultz saying that if you want the classical theorems of, like, for example, the topology of the complement of the hyperplane arrangement, the ways in which we place subspaces in the large dimensional Rn come with some signs that come from orienting the subspaces, and they come with some natural signs that somehow tell us the polymatroid does not determine the cohomology or a lot of the topological structure, but if we know a little bit more about some signs, then we can or we can determine much more of the topology. And the issue is that we don't have nice presentations or nice rings because it seems that polymatroids do not have enough cryptomorphisms. We don't have enough language to talk about them. And so the point that I want to make is that maybe by studying some of these new cryptomorphisms, one can develop the theory of orientations in a combinatorial way to actually be able to present many of these new, or many of these old theorems in cohomology. So Fechner-Ziegler and de Longueville-Schultz, which are compatible with the with this unbounded matroid philosophy. And so that's pretty much what I wanted to say. Thank you very much for staying on the first day after many, many long trips. And so if you want to have more about the details, or if you want more details about any of these things that I just say, or you're interested, feel free to come and talk to me. There's many different aspects of the theory that I would think appeal for structural results or for geometric results. So thank you very much for your attention. And I hope that I did not mess up that.
All right, are there any questions for Jose? Yes, you.
I cannot hear you.
Type B. Can you do type B?
Type B. I have no idea if we can do type B or not. I suspect that you could do something similar. I mean, I can also tell you, like what's the notion of 0, 1 in type B is not entirely clear. I can tell you that if you have positive integer vectors, you can do a similar trick and say if you take an unbounded polyhedron with integer vectors, you can decompose it as an honest polymatroid and a poset. So I imagine that there's a rich theory behind it, but I'm not sure if that's going to work. Sorry. Yeah, maybe you're close enough that I can hear. But
For the recording, anyways, for along similar lines, a generalized permutahedron is you kind of drop the 0, 1 vector condition, but the edges are all parallel. Did you guys think along that direction, like an unbounded?
Yes. In fact, so if you think about, or the notion that I want to say of polymatroid is the same, but now I have integer points instead of. So I have integer vectors, if you want, in the vertices. And if you have one of these, you can actually decompose it into an unbounded matroid. If you have an unbounded generalized permutahedron, then the canonical decomposition of cone plus generalized permutahedron actually holds. It's not very difficult to show, but it's not as canonical as what happens when you have integer points in which you can actually just intersect with the lattice and look at positive points and get something nice. Yeah, mega. Huh? So all of these are mega matroids where the rank function is 0, 1. And if you have integer mega matroids, you can also play this same game. And if you so you take the mega matrix, you intersect with the integer point, with the positive integer points, you're gonna get a polymatroid or you're going to get an honest generalized permutahedron from which you can recover the theory. But they are they are highly related.
All right, let's thank Jose again.